So not all normal modes will necessarily be able to absorb infrared light and be detected via infrared spectroscopy, or be able to scatter infrared light and be detected via Raman spectroscopy. And so what we use to determine whether or not normal modes will be active in infrared and Raman spectroscopy um, is called selection rules. These are called selection rules. And these are actually incredibly simple, it turns out. The derivation from them, we're not going to cover, but that is comes from some quantum mechanics. Um, if you're interested, I can talk to you about that offline. But yeah, so basically, different symmetry rules determine these selection rules. Okay, so symmetry rules are going to determine whether or not a normal mode is IR or Raman active. For infrared spectroscopy, for IR absorption, the normal mode that in question must have the same symmetry as x, y, or z vectors, okay, or x, y, z functions. We'll see what that means in a second here. And for Raman, the normal mode must have, that you're evaluating, must have the same symmetry as some sort of quadratic function. Any quadratic function suffices. So your options are x squared, y squared, z squared, xz, yz, or xy. So if one of these or multiple of these functions, quadratic functions, transforms in the same way with the same symmetry as your normal mode that you care about, that normal mode will be Raman active. Okay, so we can now, with this very simple rule, look at any character table. For example, here the D3D character table, and we can ask, okay, if a molecule is in the D3D point group, what normal modes will be active? What will the symmetry of the normal modes be if they are to be active for infrared spectroscopy and Raman spectroscopy? And so all we do is we look at where, for infrared, where X, Y, and Z are. And so all character tables will, or any good one, will have the linear and the quadratic functions listed on them. And so you can see that both X and Y, they actually transform together because this EU is a two-dimensional thing. So irreducible representation. So two functions have to transform together. But because X was there or because Y is there, either one of those is enough. You know that if you had a EU normal mode in your molecule, it would be IR active. Similarly, because the A2U irreducible representation transforms as Z, you know that if you had an A2U normal mode, it would also be IR active. So you're looking for X or Y or Z or both of them, doesn't matter. Okay. What about Raman active? Well, here we look for quadratics. Well, you can see our quadratics here. And so, yeah, it looks like four different functions, two sets of two quadratic functions transform as EG. We don't really care as long as one of them transforms. That's enough to tell us that an EG normal mode would be Raman active. It would appear in the Raman spectrum. Similarly, we have some squared values. We have x squared plus y squared. That's good enough. We have z squared. And so A1G is going to be Raman active. So, in summary, we have two we have two normal mode, two symmetries that could give rise to IR active normal modes for any D3D molecule. And we have two symmetries that could give rise to to Raman active normal modes in D3D symmetry. And if you have A2G or A1U normal modes in your molecules, those won't appear in Raman spectroscopy or in IR spectroscopy. So we call the A2G and A1U normal modes vibrationally silent, okay? What about C5V? Let's just do another example. So pretend you have a C5V point group. Which normal modes are going to be IR and Raman active? Well, the IR ones are going to be any of them with X, Y, and Z. So A1, that has Z, so that's going to be IR active. If you had an E1 mode that has X and Y transforming as it, so that would also be IR active. And then for Raman modes here, there's 3 different ones. The A1 mode, the E1 mode, and the E2 mode. Normal modes of any of those symmetries would be Raman active because you have quadratics. X squared minus Y squared, that's good enough. XZ, that's good enough. X squared plus Y squared, that's good enough, okay? A2 would be vibrationally silent. What about C2V? C2V molecules, which ones are gonna be Raman and IR active? IR active, well, you're looking for X or Y or Z. And so there's X, Y, and Z. So that tells you if you have A1, B1, or B2 normal modes, those are going to be IR active for a C2V molecule like water. And all of the modes in this point group are going to be Raman active because there's quadratics that transform, quadratic functions that transform as all these symmetries. So this is a really straightforward way that gives you really powerful information about what is going to be in a Raman spectrum or an IR spectrum. And you can hopefully see how chemists can use this to then determine the structure of the molecule. Like let's say they're trying to figure out if something's tetrahedral or square planar. Well, they would look up the corresponding point groups for those different geometries, which are TD for tetrahedral and D4H for square planar. And then from that, you know, they could look, all right, well, how many normal modes do I have appearing on the infrared spectrum? How many normal modes do I have appearing on the Raman spectrum? A really fast way to do this is to use this sort of theorem that tells you that if a molecule is in a point group that contains the inversion operation, none of the IR active modes will overlap with the Raman active modes. In other words, there won't be any coincidences between the Raman spectra normal modes and the IR spectra normal modes. So let's look. So we're looking for, so that's for inversion. Okay. So let's see. D3D, that had inversion. Okay. This has inversion symmetry. And look, sure enough, the 2 Raman modes don't overlap. They don't have share any of the same symmetries as the IR mode. That's what our theorem tells us. If you have inversion, the IR normal mode symmetries are going to be completely separate from the Raman normal mode symmetries. C5V, there's no inversion, okay? So the theorem's not gonna hold. You have overlap. You have these double circles here for IR and Raman. C2V, no inversion. So again, you have the double overlap. So if you want, you can look through, you know, a list of the character tables either in your textbook or online, and you can check all the ones with inversion, and you'll see, yes, they're all like D3D, where you have a separate category for Raman active normal modes and a separate category for IR active modes, normal modes. You know, in the early, it was like in the 1960s that xenon compounds were first discovered. So for the longest time, right, noble gases were thought to be totally unreactive. They're totally noble. But then Neil Bartlett came and he reacted xenon with potassium PTF6, and that actually makes xenon fluorides. Xenon tetrafluoride is one of them. And so, you know, people, you can model this with via CPR, and xenon tetrafluoride is predicted to be square planar. And it turns out, you know, people shortly thereafter, after the synthesis of it, took IR and Raman spectrum and very easily saw that, you know, this was square planar because D4H has an inversion, but tetrahedral symmetry doesn't. Okay, there's no inversion. So they saw in the Raman and IR spectra of xenon tetrafluoride that, you know, all the Raman peaks of the normal modes were separate on separate energies than the infrared normal modes. So they very easily figure out that xenon tetrafluoride was square planar. So just like that, you get the structure from doing spectroscopy, and you know that was very important. It was kind of a whole new world of noble gas compounds, which is kind of cool. So, all right.